In this video, I'm going to go through an introductory handout about area moments of inertia. I've kind of already introduced it via the yardstick example, and also talking about the use of area moments of inertia in mechanics materials formulas. But still, there's some other introductory aspects of area moment of inertia that we haven't talked about. And so again, I'm going to bring up a handout and share it and then talk through that. So this is a general handout on area moment of inertia. And the general integral form of the area moment of inertia is Ix is equal to the integral of the area of y squared dA, and Iy is the integral of the area of x squared dA. So for a given area that you're trying to find Ix or Iy for, you define a dA of some kind, and there's a distance y from the x-axis up to that dA, or distance x from the y-axis to that dA, and you're squaring that distance. So again, area moment of inertia is a function of the area, but it's a function of the distance squared of that area from the axis of interest. We'll say more about these integrals soon. In this class, we're mostly talking about area moments of inertia, and those are used commonly in mechanics materials. But in dynamics, you'll use mass moments of inertia that's basically defined in the same way. And so a mass moment of inertia is I about a particular axis is equal to the integral over the mass of r squared dm, where dm is a mass element with some mass density rho times a dv. For example, if you're doing rotational dynamics, the net torque on a rigid body produces an angular acceleration alpha that's proportional to the mass moment of inertia. So Ig is to rotation. It's the body's resistance to rotation. That's an analog to like a body's mass in terms of its resistance to linear acceleration. So mass moment of inertia is very similar to an area moment of inertia. Area moments of inertia are used in mechanics materials when we're calculating stresses in beams, beam deflection, stresses and angle of twist in shafts and torsion. We also use the area moment of inertia, the minimum one, to determine a column buckling formula. Again, if you look at the properties of the area moment of inertia, one of the huge properties is it's a function of the distance squared from the axis of interest. And so we have three different shapes here: an I shape, which is 1, a rectangular shape on its side, which is 2, and a rectangular shape oriented this direction, which is 3. All of these have the same cross-sectional area, but they all have different area moments of inertia about the x-x axis. So the 2 shape, more of this area is close to the x-x axis, and so his Ixx is the smallest. Area 3, he's oriented vertically. His area is a little further from the x-x axis, and so his Ixx is larger than the 2 case. Finally, the 1 case, again, the same cross-sectional area as the other 2, but now we've taken a maximum amount of that material and moved it out to a top and bottom flange, and we left just enough material in that web to provide stability to the beam and to provide strength in shear, which is another story. But because we've moved this area a maximum distance away, its area moment of inertia about the x-x axis is larger yet than 2 and 3. And so again, that's the great engineering quest to achieve greater strength, greater stiffness, greater utility by using less material. And so area moment of inertia is a critical way we do that. So I is different about every axis that passes through an area. So if you have a general area, you've got an axis 1, an axis 2, an axis 3, an axis 4 that at some angle, or an axis 5 that's some other angle. In general, the area moments of inertia about all of these axes will be different than one another. In general, an axis about the center of the area, in general, is going to have a smaller I because all of the area is closer to that axis. And so remember, I about a given axis is equal to the integral of a distance squared times that area. And so if that axis is close to the area, all of the distance squareds times the dAs, those terms are going to be smaller. And so again, if you look at this shape, 2 passes close to the centroid of this area. So I about 2 is probably going to be small. Well, it is going to be smaller than an I about the 1 axis or an I about the 3 axis. And also there's I about these rotated axes 4 and 5. So later in this unit soon, we're going to calculate product of inertia, and then we're going to calculate I values about axes that are rotated from our original axes. That's called transformation of those numbers. And so you will learn how to do that in this unit. If you know I about one axis, then you can use a parallel axis theorem, which I abbreviate PAT, to find I about some other axis that is parallel to the original one. Super important. One of those axes must be a centroidal axis. If one of them is a centroidal axis, then you can find I about some other one. So here's the general formula. So I about some axis of interest is equal to I bar. And usually if you see I bar, that's the I about the centroidal axis, plus the area times the distance squared from that centroidal axis to the axis of interest. So I bar again is a centroidal I, and then AD squared is called a transfer term. It's a term we use to transfer an area moment of inertia from one axis to another. Note that I bar is a minimum for an area at the centroid, which we already noted. And as you move away from the centroidal axis, I increases by the factor AD squared. And so again, the further away you go, the number gets larger. One more point that I'll make here is that area moment of inertia is a positive number because you're squaring the distance. If the distance is positive or negative from our axis of interest to the dA, because we're squaring it, the I will always be positive. Later, we're going to be calculating a product of inertia, which is a different animal, and PLI will sometimes be negative, which you will learn. Some additional properties of the area moment of inertia. We're most interested in the centroidal moments of inertia. It's the centroidal values that are used in the mechanics of materials formulas. But moments of inertia along the x and y axis are easier to calculate. So most of your problems will ask you for I about the x or the y axis. If you ever need to move them to the centroid, then you'll use the parallel axis theorem to take you up there. Soon, actually, one of the later lectures today, we're going to derive the parallel axis theorem because it's important for you to see the derivation, to appreciate how to use it. So the focus of today's lecture, these current videos, are on moments of inertia by integration. But next class, we will also work on a number of examples of moments of inertia of composite areas. So a composite area is basically a shape that is a composite of subareas of known shapes. For example, if you look at this shape here, there's a triangle, there's a rectangle, there's a half circle, and there's a circular hole. And so we're going to be interested in finding I about the x-axis or y-axis for this composite shape. It's actually pretty straightforward. You're going to use the parallel axis theorem to do it. And so, for example, for this particular shape, the I about the x-axis is the sum of the parallel axis theorem terms for each shape. So each of these shapes, like this triangle, will have an I bar about its centroidal axis, and then it has an area, and it has a distance from its centroid to the x-axis, and you're going to square that distance. With this rectangle, it will have an I bar about its centroid. It has an area and a distance from his centroid to the x-axis, and so on. And so the same with the y direction. You're going to take I centroidal I's for each of these shapes and then transfer those to the y-axis. You'll learn this soon, but if a shape happens to touch an axis, for many shapes, we actually have an I base formula for that shape. And so if for this rectangle, for example, touches the x-axis, rather than using an I bar plus AD squared for this guy, you can just use the I base for this rectangle. Or this triangle touches this y-axis, you can use I base for him about the y-axis. But about the x-axis, you have to use the transfer term to take this guy down to here. More on that later. So you'll need to know, and you need to have tabulated the area moments of inertia for common shapes. And so a rectangle about its mass center or about its centroid, I bar is 1/12 BH cubed, and I base is 1/3 BH cubed. We'll explain this more in a moment. These are the values for a triangle, for a circle, for a half circle, for a quarter circle. And again, we'll use these more when we get to centroidal shapes in our next lecture, but they're here for your reference for now, but you need these. So this is an introduction to just some of the properties of area moment inertia and some of the problems that you're going to work and some of the equations, for example, the parallel axis theorem that you need to know.